You know, there's some relatively easy vector addition, you know, where you have a vector. You know, you have a vector like this plus a vector like this, which equals a vector like this and a vector like this. And we remember, because we all have used our brains since then, that when we have vectors, we need to use trig, right? Trig in geometry when we add and subtract these vectors, right? And by the way, don't forget that if we have this vector minus this vector, what does that look like? Okay, this is the same as this vector plus this vector, right? The opposite vector. Yes, Amy? All right, so this will equal that plus that, right? For our result. Got it? Now that turns out to be kind of important because sometimes it's convenient for us, you know, we add this vector plus this vector. Let me rewrite this one. This vector plus this vector equals this. So A plus B equals C. Okay?
Now it's relevant.
Now you remember?
No, I already remembered, but now it's relevant.
Okay, yes.
What's the magnitude of it?
Magnitude of what? Which?
Like if you're at 3 parts. Yeah. Like on question 1.
Question number 1?
Yeah, that works.
What is the magnitude of the resultant vector? Okay.
I remember it's like it's a square root thingy.
Ah, okay. Got it. All right, hang on just a second. Well, I'll just tell you right now. Here you go. All right, these vectors all have, since they're a vector, remember they're different from scalars, because scalars only have magnitude, which is just a number and units which tell you what it is, right? Tells you how big something is. Like $12. $12 is different than 12 euros, so the unit's important, right? Or 12 diners, or 12 drachmas, or whatever, okay? So the unit makes a difference. In vectors, a number with a unit is not enough. You need to tell the direction. Now, if it's in a one-dimensional environment, like everything is in the x direction, then it's okay to just say, designate one direction as positive. Say, like to the right is positive. Okay? And so then if you said 10 meters per second and negative 10 meters per second, you can tell the difference between those two, right? What's the difference? Directions. One is that way and the other one is this way, right? One's positive and one's negative. Okay, but if we're dealing with a two-dimensional environment like this, okay, not just x or not just y, okay? If we have just x like this, then we've essentially turned this into an algebra problem, right? Then we can solve things with algebra. Like for instance, if I have plus 10 meters minus 3 meters, and we're talking about the x direction, well then I know that I've traveled, I've displaced 7 meters that way, right? Yeah, because you just subtract them like regular numbers, right? Regular algebra. Okay, but if it's in a two-dimensional environment like this, we get something to the right and something up, and we get this right here, okay? There are two ways to describe this, okay? Like for instance, let's say that this is 3 meters to the right and this is 4 meters up, so this is 5 meters that way, okay? There are two ways to describe that. One way to describe that is that, well, tell me, how do I describe that vector completely? So everybody knows what it means. 5 meters, which way?
3 degrees.
3 degrees?
50.
Well, let's see, yeah. I have a 3, 4, 5 triangle, right?
Right.
So you could use your trig to figure it out if you didn't remember a 3, 4, 5 triangle, but that turns out to be 53 degrees. So my answer would be 5 meters at 53 degrees, right? That'll do it. Okay, there is another way to describe that as well, and that's to write it in component form. We'll talk more about this later. And that would be just to say that I have 3 meters in the x direction and 4 meters in the y direction. And to designate x and y, believe it or not, they do this. 3 meters in the I direction plus 3 meters in the J direction. Have you seen that before?
Yeah.
Okay, where did you see that? You see that in calculus?
Yeah.
Okay, the I, J, K designation, unit vectors? Okay, good. So you've seen that before. Both of these are equivalent statements. This is technically in polar coordinate notation. This is technically in Cartesian coordinate notation, component notation. Okay? Either way. All right, but I got sidetracked. Any other questions on that? Are we doing okay?
Yes.
All right.
Mr. Brown?
Yeah.
Say it loud.
Yes.
Okay, so this is from number 5, but like they want you to find the component that makes the resultant if they give you one component. But then like what happens if you get like a negative number? You can't stir with that.
In number 5. No, wait a minute, hang on. Did I answer your question for number 1? Hang on, one quick question. I just remembered. I don't know if I fully answered it. This is the magnitude. If they ask for the magnitude of the vector, that's it. Okay? Magnitude and direction. In polar coordinates, you get magnitude and direction. In Cartesian coordinates, you get the components. Okay, now your question is in number 5. So you want to find the component?
Yes, because it says find the angle of the second displacement measured. So I'm assuming if they give you one component, then they give you the resultant, and they want you to find the other component. Is that right, or am I not reading?
Yes. Okay, so what they're doing is they're giving you a component and the resultant. Okay, excellent question. Which leads me right into this. Okay, does everybody see this statement right here? A plus B equals C. One component, second component, resultant, right? Okay, we can handle this just like algebra. I want to know the second component, okay? So like, what if it was like this instead? All right? So this was my unknown. A plus unknown equals resultant, okay? How would you handle that in algebra?
You do like the same here, but you solve for B.
You would just subtract this one from the other side, right? So you can do this. The vector B, which is a component, equals the resultant, which is vector C, minus the component A. All right? Now, that's, say like this. Say I walk 3 meters this way plus something equals 5 meters to the left. Okay? All right, so what's this one?
8 meters to the
8 meters to the left, right? Or 3 meters plus, positive 3 meters, plus our unknown equals negative 5 meters. You'd subtract this from the other side, you'd get the question mark equals negative 5 meters minus 3 meters, which equals negative 8 meters. 8 meters to the left, right? Okay, we're going to do the same thing here, but our issue here is that we have something in two-dimensional space, right? So how do we add vectors that are in two-dimensional space? Like, for instance, what if I have a vector like this plus a vector like I don't know, like that. All right. Now visually, it's pretty easy to add those. Vector A plus vector B. It's going to give me something like this. This is vector C. A, B, and C. Right. But mathematically, how do we do that? How do we do it? Separate them into components, right? So I got to take this one, and I got to split it into its x, and this one into its x, and y. You can't tell the difference between those, can you? Y and y components, right? So I have a positive y component here, a negative y component here, and I have a positive x component here and a positive x component here, right? So what I end up with is an x plus an x and a y minus a y over here, right? So you got to split them up into components. So I'm going to end up with this piece plus this piece, our x1 and our x2, add them up. And then I'm going to have a positive y, and then I'm going to have a negative y, right? And it ought to, my diagram isn't exactly right over here, but I'm going to end up with a little side over here, right? Because this plus minus this one is going to end up with those subtracting from each other, and I'm going to end up with something small, something like that. So it looks like my drawing over here is incorrect. Should be a little bit up compared to what I have here, right? So it looks like my final vector, my resultant, will look like this then. Does that make sense? All right. So this should have looked like this. Yeah, there we go. All right? All right, now, we're going to do that in reverse over here. Okay? We're going to do that in reverse over here. So let's just do one quick. Let's say that this is right here. This is 10 meters at 45 degrees, and let's say that this is 8 meters at 30 degrees this way, which would be the same as 8 meters at what angle in polar coordinates? 0, 90, 180, 270, 360. 360 is all the way around, right? But we're not quite to 360, are we? We're in the fourth quadrant, 30 down. So that would be 330, right? Does that make sense?
Yes.
Okay, so it's, remember our polar coordinates, x, y, 0, 90, 180, 270. This one's pointing into the fourth quadrant at 30 degrees this way, so that's going to be 330 degrees, okay? Or sometimes you'll see it as 30 degrees south of east, right? Something strange like that. Or even occasionally you'll see negative 30 degrees. So instead of going the correct way, you go in the opposite way, right? Just in case. All right, so here you go, everybody. If we go A plus B equals C, we're going to have to find out all these components, right? Let's do that quick, and then we're going to do it in reverse. And we'll find one of the components instead. All right? So A plus B equals C. Here's how we do it. This is vector A, and this is vector B. Okay, what are the components of vector A? Let's have these two tables over here tell me the components of vector A. Let's have these two tables over here tell me the components of vector B.
So the easy one.
Yeah, I did give you the easy one.
That's fine. 5 root 2.
Oh, give me a decimal. I'm a decimal kind of guy. Courage hurt my little brain. 7.07 and 7.07. Well, that was easy. It's too easy. All right, what'd you guys get?
Nothing.
Nothing?
I said not there.
Well, I know that y is going to be 4, right? 4? 4? Negative 4. Because it points into the fourth quadrant, right? Negative 4. Because it's negative y. Okay, so what's x?
6.928.
6.9. 9 what?
3.
3. Okay, sum them up. This one becomes 3.07. What's this one? 0, 0, 14. Wow, look at that. Okay, that's what C equals. All right, so tell me, what's the magnitude and direction of vector C? 14 squared plus 3.07 squared, or just 3 squared, right? Square rooted, what is that?
Calculator.
What is it?
14 squared plus 3 squared, square root.
14.33.
It's 14.33.
14.3 is, let's just say, 14.3 meters at what direction? Okay, it's going to be in the first quadrant, right? It's going to be a small angle. Less than 30. You guys are slow. Come on, hurry up. 12?
12.37. Round 12.
Okay, approximately 12 degrees, right? Okay, let's do this in reverse. Because problem number 5 says they give you something like this.
Do they not ask you for magnitude because they know it's like going to have that negative? Hey.
All you need to know. All you can all the time.
Well, you don't have to imagine, that's right, though, I said it's negative, but it's not. But it's because
Huh?
the resultant is smaller than, it's like, magnitude-wise, the resultant is smaller than the first.
I have one of the other ones going in the opposite direction. So I can
Right.
use
Yeah, but when you try to magnitude, it's different.
They're gonna be the same, right?
Try to find magnitude, even if like it's not really hard, try to find magnitude.
Okay, this is similar to number 5, okay? Probably made it a little bit harder, but that's okay. So here we go. Let's say you walk 10 meters at 63 degrees, then you walk with your eyes closed in some direction. They spin you around, you walk for a while, and then you finally stop. And when you stop, you're 20 meters away from where you began at 143 degrees. Okay? So here you are. You started here. You walked, 10 meters that way at 63 degrees. And then sometime later, you ended up out over here, 143, which is somewhere out here at 20.
What if that's smaller?
At 143 degrees. So this is your resultant. Okay. Oops, wrong way. Resultant. So where is vector B? It's this one plus our question mark, vector B, equals the resultant, right? So it's from here to here, right? So this is our unknown vector, or vector A, B, and C, right? Okay, so how do we work backwards to get that one? Now, if you wish, you could use law of sines or cosines, probably to figure that out. Because this is 143 degrees. Now, in fact, it might be easiest to solve it with law of sines or cosines if you remember that. Okay? All right. Now, another foolproof method, though, is to use components again, right? So let's do this. Here's vector A, here's question mark, and here's our resultant, vector C. Okay? X and Y. All right, let's do it again. These two tables over here give me vector A in components. These two tables over here give me vector C in the components.
For X, for A is 4.54.
4.5, let's just do 4.5. Carry one decimal, that's fine. And 8.9? Okay, everybody check. Let's make sure that's correct. Not that I don't trust you. It's just we always check. Right? That's why we work with others, so that we can always check.
Vector A is 63 degrees, 10 meters.
Y is correct? All right, so let me check X as well. All right, how are we doing over here? We got vector C, we got the resultant. What is it?
Not yet.
Not yet?
It's all good.
All right. We have,
Negative 2.9.
wait a minute, which one is which? Which one are you giving me?
X.
X is what?
Negative 2.9.
Okay.
What? Y.
Negative 15.
Negative
Calculators.
15.
Guys,
Oh, negative 15?
like calculators.
We have this thing. Yeah, it's negative 15.
And then the Y is 12.
Negative 15.9?
Then do you know?
97, so it's negative 16?
Yes.
If you already knew the answer, why'd you ask us?
I didn't know, I don't. All right, what's y?
And then
12 on the nose?
12.04.
12.04.
All right, and positive. Does this make sense?
Yes.
Is this in the second quadrant?
Yes.
All right, that's x, y, and this is x, y, both positive, first quadrant. Okay, that checks. Okay, please check. You know, do that little, what we used to call an engineering idiot check to make sure that you're not an idiot. Because sometimes it happens to all of us. Okay, now, so what goes here and what goes here? Yes, look, all you're doing is subtracting now, right? You're subtracting the vector. So what you're really doing is subtracting this vector from this vector, right?
Yes.
So that means taking the negative of this and adding it to this one, right?
Yes.
So what is this one?
Minus 20.
Alrighty then.
Minus 20.5, and what's this one?
3 point, are we doing 3.1?
3.1.
What are we subtracted?
12 minus
Because what we did is, remember, A plus B equals C, or B equals C minus A, or negative 16 minus 4.5 equals negative 20.5, or 12 minus 8.9 equals 3.1. You see how we're doing this algebra, and it just looks weird because we're doing it in geometry in 2 dimensions, right? It's not a big deal. Just got to remember what you're doing. It's just a lot of times for some of you, well, for most of you, at the beginning, it helps you to do this little table to remind you of what's what. So don't get confused, because it's easy to get confused. Now, some of you will prefer to draw a diagram like this, and you'll draw the components on here, and you'll draw the components on here, and you'll work kind of visually. If you're a visual learner, or even a tactile learner, this is probably better if you do this. Draw the components on here, and then figure out from that what these 2 legs of that triangle are. That little diagram for a few of you is going to be genius. And others of you are like, huh,
Yeah.
I prefer this. I like the table. If you like the table, do the table. If you like the diagram, do the diagram. Okay? And with practice, you'll be able to do it either way. Okay? Because this is, for me, this is easy. Because I see this length and I see this length, so I know that this right here is the long one minus this one. I know this one is the addition of these 2. Voila. I got my 2 legs of my triangle, right? So it's up to you which makes sense to you. It doesn't matter which makes sense to you. Just go with what works. All right, does that help you with number 5? Okay, it's just subtracting vectors. Okay? There is a problem on our next e-homework that's due next Tuesday, I believe. Okay? And it is a problem where there is a monkey in a tree.
Oh, no.
And it's swinging.
And no, not swinging.
No.
Not the swinging monkey.
It's still a monkey. It's still horrible. If it's a
We just
monkey, I
love
get
the
it.
monkey.
I love that he falls
With a normal
he
horse.
falls to his death, but he gets a coconut just
What are coconuts doing in
Monkey
trees?
problem last year that I
Coconuts grow in trees?
All right, we had a monkey in a tree.
Coconuts grow on palms.
There's like a boy or a girl down here that has a coconut. And they toss the coconut in the air with an initial velocity from an initial height, certain distance off the ground. Okay? And the monkey drops out of the tree and catches the coconut, steals the coconut from the poor little boy. Poor little boy.
You just want to
And then falls to his death. No, monkeys are resilient. Okay, the question is where does the monkey catch the coconut? Agitated. And they decide to launch a nuclear bomb at us because they have missiles now. And let's just make it easy as possible. Let's say the nuclear bomb is, let's say 1,000 feet off the ground.
I like the monkey better.
That's pretty
Yeah,
close.
I'm like the
Okay?
That's pretty close for a nuclear bomb.
Yeah, that's really close.
Yeah, we're dying now.
but it's a happy nuclear bomb.
Like 100 people.
All right? And I'll even make this easier. Let's say that it's beginning at a velocity of 0 because the North Koreans, you know, they're a little light on some technology, so they dropped it from a balloon. All right? So it starts off at 0 velocity, all right? Now down here we have our anti-nuclear bomb missile. Okay?
Look how small it is.
It doesn't need to be big, it just needs to be fast, right?
Yeah, still pop it.
All right. It starts also at 0 velocity, and it starts from the ground, okay, or x equals 0 here. We'll call up positive, okay, and let's say that this little dude can accelerate upward with a positive acceleration of 20 meters per second squared.
That's pretty fast.
That's a lot of acceleration, all right? Okay, now I want to know, where does our little rocket hit the big nuclear bomb?
What's
When you
is the
show
bomb
velocity,
simply going on gravity, or
Yeah.
is it also accelerating?
It started.
All right, let's say that it's just falling. That's an excellent question. So what do we know about this one? We know x naught equals 1,000 meters, right? We know v naught equals 0. I should have put 0 there, sorry. It starts from rest. We're making the problem a little easier. All right, and we'll say that its acceleration is 9.8 meters per second squared. I made a mistake. What did I do? It's important to make this negative because that's downward and we're calling upward positive, right? So
Is
please be
acceleration-
careful. What's that?
The acceleration of the little rocket including gravity?
Yes. Well, I get that question all the time. Does the 20 include gravity? And the answer is yeah, that's already in there. If they say it's 20, you don't have to add the gravity on it. Okay, what do we know about this little dude? We know that x naught is 0. We know its v naught is 0. I didn't write that down again. And we know its acceleration is 20. All right. How do we mathematically model that? Yes.
You set equations like you know that the missile is falling at 9.8 meters per second, and it's 1,000 meters up, so 9.8 x squared plus 1,000 is equal to 20 x squared. And then you just solve for x. That gives you seconds. Solve for the distance down.
All right. And the key part of why that works, the key part of why Andy's explanation works is because when the two meet, the x for the missile and the x for the bomb will be the same. And when they meet at the exact same time, right? Okay, it's not like they're at different places at different times. They're at the same place at the exact same time, right? So what we need to do is find where this one is at any time as a function of time, where it's at. Where is this one at as a function of time? Okay, can you write those two equations? Can you find an equation for where each one is at any given time?
Oh, that's what it is. That's so cute.
So it's 1,000 divided by 14.9.
And then the 10 plus
Okay, is this what we get?
I got 8.1. That's what I got.
Okay, these are two equations.
Yes.
Okay, now, once we get the two equations, that is the hardest part, right? That's where all the brain power is required. Once you get to this point, you just set the two equal and solve for time or solve for x. I would guess that you would set this equal to that, solve for time, and then plug it back in to find x, correct?
Why negative 4.9?
Why negative 4.9? Because the acceleration is negative 9.8, and you divide that by 2.
What are we solving for at the very end?
Oh,
We're solving for where do they collide and how long does it take.
So you can plug the time to
So what else do they kiss?
671.
671 meters?
Yes.
Okay, it gives you the exact location. Then the time it takes?
8.2 seconds.
8.2 seconds. Now 671 meters is not a lot of distance off the ground, but if it keeps the nuclear bomb from exploding by hitting it before it detonates, it's all good, right? It's better. It's not all good, it's just better. All right. Now, could we now find the velocity of each when they collide?
Yes.
Yeah, because now we know where they're at what time, we know the initial conditions, so we could find their collision velocities, right?
Yes.
Okay, and there you go. Now the monkey problem is exactly like that. You will have, in this case, the acceleration of the monkey here is negative 9.8. The acceleration of the coconut here is also negative 9.8. But it'll be a similar problem, okay, where they are colliding. They both have the same negative acceleration, right? Okay, got it?
Yeah.
That's an intersecting path problem. It's a good bet that if they have a kinematics problem on the exam, if it's gonna, that's one of the things they'll throw in there just to see if you kind of understand your kinematics, all right? All right, so you could actually solve this graphically as well. Real quickly, if you don't mind, on your calculator, will you plug into y number 1, plug in this equation, and y number 2, plug in this equation, and see where they intersect?
Oh,
And that will also give you the same answer, right? That's another interesting way to solve it. For some of you, that's a really nice way to solve it. Okay, makes a lot of sense. Okay? There you go. Okay.
Yes.
Let's go to rotational motion.
Well, that's not fun.
All right, here you go. This Blu-ray disc is rotating. Which of these spots is moving the fastest? Spot A, B, C, or D?
A.
C.
D is
Oh, wait, D. The one
I wanna
that's
say
closest
D.
to the.
I don't know.
That's the answer.
Oh, wait, D.
C.
C.
What, C?
D isn't moving.
No, it at the same time it has to cover a much larger distance.
There you go. Is this better?
This is A, it's A.
This is true.
A is here,
C, it's like, and then
B is here, C is here, and D is in the center. So where's it going fast?
Hey.
It's dry erase and it's on the front side.
in the same amount of time, A covers like.
Won't they come off?
I'll take the blank.
You will have to.
It's okay.
It's like my favorite.
Oh my gosh, it's harder.
You're gonna like break it and rub off all the memories.
All right, A.
It's just a red dot, it's okay.
All right, A.
We can see the smudge more than.
Shut up. B, C, and D. Where's the fastest?
A.
What do you mean A?
I thought it was.
Why A?
It has to cover most distance at the same time that C covers.
Because in one when it makes one circle, A travels the greatest distance. Is that what you're telling me?
Yes.
And they all travel
At the same
oh,
time.
oh, they all cover a circle in the same amount of time,
Yes.
Not the same.
but not the same circumference, right?
Yes.
So for velocity equals change in distance over change in time, the circumference is 2 pi r over t, and A has the longest radius. Ah, okay, that sounds good, except you're all wrong.
Really?
Well, then they are the same.
They're all the same. They're all traveling exactly the same speed.
Because the one in the middle takes longer.
Unless it stops at like 359 degrees.
They're all traveling the exact same angular speed.
But angular velocity.
angular velocity. They're all traveling the exact same angular velocity because they all cover the same 360 degrees
Oh, I get it.
But
in the same amount of time.
But they have to
So-
balance out, so the
Change in angle over change in time is all the same. Okay, now, do you see that we're arguing about two separate things, right?
Yes.
Okay, there's a such thing as translational velocity and or translational motion, which is what we've discussed so far.
All your fault, Ben.
Translational motion is x, v, a, and t. And angular or rotational motion. Rotational motion is, instead of x, how far you move translationally. In fact, let's back up a bit. It's how far you do what?
Angle.
How far you turn rotationally. That's theta. Okay? All right, because there are two types of motion. There's this type of motion where you translate, okay? And then there's the type of motion where I can't do it here. I'll do it this way. I'm not going to do a cartwheel.
You should. That'd be really awesome.
No, my hair might fall off.
No, my glasses try to do it.
My glasses might fall off. What's that?
Try to do a cartwheel and stop in the middle.
And then do a push-up upside down.
Yeah. On one
Out at the same time.
Not
it's
a
gonna be
problem.
really easy.
Shannon, have you
Yeah, right.
Do that one.
Was that the necklace thing?
That's rotation.
All right. Shh. We're getting off topic here. All right. Okay. So we have translational motion and we have rotational motion. Is it possible to have both at the same time?
Yes.
Sure. That happens all the time. Gymnastics would be really boring if you could only have one or the other. They run, and then they stop, and then they spin, and then they run, and then they stop, and then they spin. They do both at the same time, right? In fact, they'll rotate about multiple axes, or different axes, like this way, or this way, or this way, this way.
Power if they do both.
What's up?
Rotational and translational at the same time.
It's really easy.
Deduction.
That's right. Okay, this is angular displacement. This is translational displacement. Translational velocity, angular velocity. Omega.
A crazy W.
Yes, a 3 on its side. A very tired 3.
A dead.
A dead 3.
Aw.
All right.
But
Stop. We're on tape. It's going to be saved for posterity. No pun intended.
Oh, please, please.
I'm cracking myself up. All right. Angular acceleration. Oh, translational acceleration. Angular acceleration is alpha.
It isn't alpha.
It is alpha.
So we
The symbol for angular acceleration is alpha.
On rotational motion.
Yes.
don't think about it too
You're
much.
making it too complicated.
Just
On the nose. Okay. Translational time.
time is the same.
Time.
Dudes, time is a scalar, right? Time is time.
Yeah.
These are the same.
Well,
There's no such thing as rotational time because time is not a vector, right? A scalar is a scalar is a scalar, no directionality. Okay. So there you go. Now let's make this as simple as possible.
Yeah.
Everything that you've learned about translational motion has an angular equivalent. So like for instance, if you had these equations, x equals x naught plus v naught t plus 1/2 at squared, what's the angular equivalent?
Theta equals theta plus omega t plus
Omega naught t.
okay, plus 1/2 alpha.
There you go.
I just bypassed like.
What if I had V equals V naught plus AT? What's that?
Omega equals
Omega
omega naught.
But alpha T.
Omega naught.
It is funny.
The next transformer.
V squared equals V naught squared plus 2A x minus x naught. Almost said T.
Omega squared.
There's something fishy about that sign.
Yeah, oh, that's cool. That's my favorite.
There you go. They're the exact same equations. So let's do this real quickly. Let's say you have a rotating device here. Okay, here's the axis. All right? And it's rotating about that axis. And it begins at theta naught equals 0. Okay? And let's say that it spins for a time of 30 seconds and it accelerates at 2. What are the units on these things? Oh man, let's go back to our math. What's the connector between these? All right, you remember this from what, pre-cal, I guess? If you move from here to here in arc length S, okay? And that's theta, this is R, right? Okay? So how are these related? What's the equation that relates these three?
Oh my god.
S equals
1/2 theta
What?
It's the definition of a radian. How do you do it? How do you get a radian? Where'd it come from?
It's a good question.
2 pi.
Why is it 2 pi r? Oh, why is it 2 pi
Circumference
radians
divided
to
by-
the circle?
Something.
Just Dr. Wilson's fault.
That's okay
Dang!
too. I'm sure.
No, we've
Dr.
learned
Wilson is
it.
downstairs.
We've learned it, I just
All right.
don't remember it.
So we'll just say.
Don't make me sad.
What's this?
What's
Too late.
I was
Right?
thinking that honestly.
Oh.
Seriously?
Yeah.
I was gonna tell you that eventually.
And that's it.
So we have meters divided by meters gives us no unit. And since we don't like no unit, because we don't know what no unit is, we give the nothingness a name, call it a radian.
Wow.
A radian is really a unitless unit. It's just a thing so we know what we're talking about. Okay? So we know exactly what we're talking about when we're not having any units.
I wish you'd never told me that. I'm happy just knowing it's a radian.
It's a radian.
Okay.
Well, the thing is this, though, because you're going to see this. The connector over here is that theta equals x over r. Or you could write it the other way, that x equals theta r, right? Okay? And the problem is that a lot of people put in radians here and meters here, and x is not a radian meter. It's just a meter, right? Because a radian is just a nothingness,
Okay.
right?
Okay.
So the radian disappears.
Because it was never there.
Because it was never really there to begin with.
Oh my god.
Awesome.
Right.
I want to
The
do
philosophy.
So a physics teacher teaches, and nobody's listening. Is anyone really listening? All right, so here we go. What's the connector between these two? Can you figure that out then?
It's a radian per second.
That is true.
Second.
This is a rad, so this is a rad per second, and this is a rad per second squared, right?
Right.
Making it round.
So this is a meter per second squared. Can you infer then how you connect velocity to?
Well, is it just the same thing? So theta. Oh, yeah.
What?
Well, that's.
Need that green pen again.
I'll show you how that occurs, okay? I just want to start this table so that you see it. Oops. Those are the connector equations. All right, we'll get back to how that occurs in just a minute. Because what I got here was that we don't know what this unit is, right? What is the units for alpha? Rads per second squared. Okay, will you tell me then, after 30 seconds, will you tell me what's the angular velocity of this disk? And how far is it turned?
60 radians per second.
So I want to know what's its angular velocity at 30 seconds, and how far is it turned at 30 seconds? We need the beginning velocity. Excellent question. Is it 0?
Yeah.
All right, I'll say it's 0. Starts from rest. I thought I said rest, but I didn't write it down. Okay. Do we have a constant acceleration?
Yes.
Yes. Can we use the constant acceleration equations?
Yes.
Yeah, so we can use the rotational equivalent. So here you go. I want to know what omega is at 30 seconds. So omega naught plus alpha t. That's 0, so it's just 2 rads per second squared times 30 seconds gives me 60 rads per second. Okay, so at 30 seconds, 30 seconds, it's going at 60 radians per second. Okay?
Okay.
60 radians per second. So where is it located? Actually, that's not a good question, right?
No.
Because it's not translating. How far has it turned? Okay? So let's say what? Theta equals theta naught plus omega naught t plus 1/2 alpha t squared. So it begins at 0 and 0. So we end up with 1/2 2 rads per second squared times 30 seconds squared. So that's going to be 30 squared, whatever that is. What is that? 2,000 what?
No. 900.
Never mind. Fine.
Uh-oh.
900
Let's see this table, not that one.
Having a senior moment? I think we're all going to have a lot of senior moments.
I'll fly 5 instead.
What units? Rads. Okay, I don't know what 900 rads are. Can you give me that in revolutions, please?
143 revolutions.
How'd you do that? That was awful quick.
Yeah.
Rads per second into revolutions per second if we wanted to. You know, something that might seem a little bit easier for our brain to understand.
I threw up on that earlier.
Yeah, if that is a Six Flags ride or a State Fair ride, that's not good.
How fast does the CD go?
You know what? That's a good question. Do you know how fast a CD goes?
Should we?
I don't remember how many revolutions that is.
Don't they go up, some of them up to 96x? So that'd be 96 revolutions per second?
Is that what that means? That's pretty
I think.
that's pretty fast.
I'm not, well, no, it's gonna be faster than that.
That's right, because the way they read that data faster is they just spin the darn thing faster.
Yeah. So you'd have to find out what the original 1x speed was and multiply it by whatever the
Right.
highest speed of the drive is.
Right. Years ago, I put a strobe on one to see how fast it was going, but I don't remember. It's been a long time. All right. We had a CD player that had a little plastic top so you can see the thing spinning, so we pointed the strobe down on it, and we dialed the strobe in until the label looked like it was sitting still. And then that told us how many flashes per second. That told us how many revolutions per second it was making. I don't remember what it was. It was something like 20-something revolutions per second. At that time, that's been years ago.
Divide it and then multiply.
No, that was just curiosity. No, I was in class and we were messing around with the strobe. That's right. Had too much eco water.
Eco peanut.
All right, so there you go, everybody. Rotational motion, we've seen that S, the arc length equals radius times theta, right? All right.
Okay.
We know that angular velocity is related to translational velocity. Okay, so let's make this connection as well for everybody. Remember that V, so there you go, everybody. Rotational motion, we've seen that S, the arc length equals radius times theta, right? All right.
Okay.
We know that angular velocity is related to translational velocity. Okay, so let's make this connection as well for everybody. Remember that V equals dx dt and A equals dv dt, or d squared x dt squared. So you know what that means. In rotational motion, it's the same way.
Whoa, wait, what?
Omega equals d theta dt, and alpha equals d omega dt, or d squared theta dt squared. Okay?
Cool.
Don't let rotational motion psych you out. It's the exact analog, exact relationship as translational stuff. The only thing it's in a weird unit. Okay?
Is there another kind of rotational motion?
Now, there is rotational motion where the whole object is moving around, where it's translating around. Like, for instance, yeah, like for like a roller coaster car that goes around a track. That's circular motion, where the object as a whole is translating around. There's not a point about which the object is spinning, right? So you see the difference? That's a really good question. Because there's a difference between this type of motion, spinning motion, and like this motion. All right? This is translational motion in a circular path. Okay? I'm not spinning about a point. Well, hang on. You could relate it that way. Okay, now a roller coaster car you can't, because the car doesn't continue around in that circle forever, right? But like, for instance, if you take a ball on the end of a string and it's spinning around, you can handle that as this ball is translating. Or because there is a point about which it is spinning, right? You could handle this as omega instead, and the relationship between the two is the radius, right? Where the linear velocity equals the angular velocity times r. Okay? So like, for instance, if you're going at 10 meters per second around in this circle and the radius is 2 meters, then your angular velocity will be 5 rads per second. Okay? So you could handle it either way, as long as there is a fixed spot about which the thing is spinning and this spot is not moving, then you can have rotational motion, angular motion. Okay? Now, there are cases where you have both, like for instance a baseball. You've got a baseball, the baseball is spinning and moving. So there is a spot about which it's spinning, but the spot is moving, right? So you have both translational motion and rotational motion. Like the planets, that's correct. Excellent, excellent. Like the Earth is spinning, but also translating around. Yeah.
It's spinning.
And then the whole thing's moving, the whole thing's moving, and it makes
It's also
you dizzy.
teeter-tottering.
Like the teeter-tottering. Yeah. Actually, it's not really doing this. It's just pointing in one space and going in one direction and going around like that. So you're actually spinning like this as you go around. You're spinning while it's
Like the moon.
Just as fast.
right. So it always faces one. The reason why that is, if I remember correctly, is because the moon is its center of mass is not in the center of the moon. and so that as it rotated, it got more gravitational force on one side than the other, which is the tidal force eventually slowed it down, so that the heavy end points towards the Earth. It's like an off-center ball, and so the heavy end of the ball points towards the Earth because gravity from the Earth pulls it that way.
Like if it was a uniform
It should
sphere, that would just be like a.
Yes, but it's close enough to the Earth that it is.
Nobody must have really thought ours out. We're gonna make this movie different.
Yes.
Why did Coriolis come back?
Why does
Does that have to do with physics?
Yeah.
the Coriolis
It's the
effect?
same thing with you going like, I just have the equator, and then it goes like that, and then it's just the way that
Did you really?
Wait, what is it?
They put a flower, I'm not sure how to fly, they put a flower in it, and it drains like clockwise on one side, I don't remember, and then counterclockwise on the other side of the equator, and then in the middle, there's it just goes straight.
So it's like right on either side of the.
Well, they have these little ports set up, and it's like instead of a road.
It has to do with the fact that the Earth is spinning, and we're on the Earth, which is a rotating object, and so.
Keep going, keep going.
All right. We had a question on the Coriolis effect, rotational. This is where we're talking about rotating objects, and the fact that, in theory anyway, water will rotate down a drain counterclockwise in the northern hemisphere and clockwise in the southern hemisphere. And the reason why that occurs is because objects travel in a straight line, but we're on a moving object, and so it appears to be curving. Easiest way probably to demonstrate that.
Yeah, you shook my head.
Like we're going. Earth moves like 900 miles per hour.
Are you serious?
Okay, here you go. Here's the Earth, equator, Santa lives up there, penguins live down here.
No, they don't.
Yes, they do.
No, they don't.
Have you seen?
They live.
What are you saying penguins are a myth and that Santa is real?
Yes.
I'd rather have Santa.
All right, now, let's say, and this is where they really discovered this. They discovered this when cannons became powerful. And they could really see it when they were out in the ocean launching these things because there wasn't stuff in the way. Okay, but you could also see this on land. It's where you would point a cannon at something and you'd shoot it and it would curve. And you're like, why? Right, here's why. Let's say you have a cannon here and you shoot your cannonball straight north. Okay? Now the deal is remember that you're on the Earth that's rotating. The Earth is rotating around this way. Your target is up here. Your target is also rotating around the Earth this way. Which one is moving faster, you or your target?
You.
You are. So here's the deal. Your cannon is shooting like this, the cannonball this way, but the cannon itself is already moving this way. So this is the net resultant of your cannon shot. It's actually moving that way when it leaves the barrel. If you are outside the Earth, you would see it travel this path. Okay? Now the deal is that this object here is also moving, but it's moving only this fast. So what seems to happen is that here you are, let's make it so that it would land on the object. So you shoot it here, but you're moving this fast. So what happens is the cannonball goes out to here, but the object has only moved to there because that's all the faster it was going. Does that make sense? So what happens is what it appears to you to look like is you're looking straight north and you shoot, and what appears to happen is the cannonball appears to curve to the right and miss your target, even though you shot straight at it. So they realized that something strange is happening. So I know that that's where they're at, but I know that I need to shoot this way to hit them. And so that's what you do. And they had all these tables. that said if you're at this latitude and you're shooting your cannonball this far, that you need to angle it off a certain angle in order to hit your target. Okay? Which works great in the northern hemisphere. If you're shooting north at a target, then you would angle your gun to the left of your target. But what happens when you go to the southern hemisphere?
You're gonna go to the right.
It's the opposite, right?
So you gotta know exactly where you are, huh?
That's correct. Now, this occurs, we see this in weather patterns, because in weather patterns we have high and low pressure systems. High pressure systems blow air into low pressure systems, and they blow straight from high to low, but because everything's moving along, they end up taking these curved paths, and they rotate counterclockwise into a low pressure system, and they rotate clockwise out of a high pressure system in the northern hemisphere. So our weather patterns and our hurricanes always rotate around this way in the northern hemisphere. In the southern hemisphere, they rotate this way. And since water is flowing from high pressure to low pressure into the hole, it will rotate, not given any other, if it's just sitting there, it should, in theory, rotate counterclockwise. But you'll see if you do this in a sink, put water in it and let it go, and do it about 100 times, it won't always go counterclockwise, because sometimes there's little eddy currents in it that'll make it go clockwise. Yeah.
So if you were to get a clockwise hurricane and a counterclockwise hurricane, would they cancel out?
Algebraically, yes.
Because like they were trying to do that for like weather systems. They were trying to like get rid of hurricanes.
By making it
Yeah.
opposite.
Extreme storm.
Well, we just push the hurricane.
Pretty dangerous.
If we just push the hurricane to the southern hemisphere, it'll disappear. That's right. We push it to some other country, and it's all good. All right, now let's talk about acceleration real quick. There are two types of acceleration, everybody.
Centripetal and
Centripetal and non-centripetal, right? Translational. Okay, when an object is a change in velocity. Since velocity is both magnitude and direction. Since velocity is both magnitude and direction, you can change the magnitude or you can change the direction, and you're changing the velocity.
Yes.
All right, if you change the magnitude, then we have what's called a tangential acceleration. That's the acceleration we normally think of, is tangential. Tangential acceleration means you speed up or slow down. Okay, that's what that means. Sometimes it's also called a parallel acceleration because it's parallel to the path you're taking. Okay? So like if I'm moving this way, if I want to speed up, I need to accelerate that way. If I want to slow down, I want to accelerate that way, correct?
Yes.
Okay. So it's a speed up or slow down. All right, this is centripetal, or sometimes called perpendicular, or sometimes called radial acceleration. And the reason why it's called perpendicular or radial is because it acts along the radius of the turn. Okay, so this is change in direction. And which way does the centripetal acceleration always point?
to the center.
Towards the center of the turn. So like for instance, if I'm moving this way and I want to turn that way, then my acceleration will be that way, towards the center. So like if I'm walking around, I accelerate that way and then I accelerate this way as I change direction, right?
You accelerate tangentially.
Yeah.
Can I do both at the same time?
Yes.
You bet.
Same thing, right?
Can you turn your steering wheel, centripetal acceleration, and step on the gas or the brake at the same time, which is tangential acceleration?
Yeah.
Yes, you can. Maybe you can't, but we can. I can't walk and chew gun at the same time.
Exactly. You know it happens.
The walking stop.
Walk, stop, chew, go.
Breathe.
Stop, chew, go.
Breathe.
No. You can do both at the same time. In fact, in the real world, things will do both at the same time all the time. Not all the time, but most of the time. All right, so here you go, everybody. Remember, how do we figure out centripetal acceleration? V squared over r is our centripetal acceleration. How do we figure this one out? Oh, sorry, dv dt. Okay? Now, when you get farther into math, you will figure out that you can determine both of these accelerations with dv dt when you do it geometrically. Okay? But since we're going to be doing this algebraically, when we think of dv dt, we're thinking of tangential acceleration. Okay? So let's look at something. If I have a car, and the car is moving along a path like this, okay? All right, right here, in this turn, is it accelerating?
Yes.
You bet. Which way is it accelerating? Well, towards the center, right? And over here, it's accelerating this way, right?
Yes.
And over this way, it's accelerating this way, right? Now, there's got to be a spot in the middle where it moves from one to the other, right? So right here, it's going straight. So right here, I only have tangential acceleration at best, right?
Right.
Okay, now here's the deal. What if I have acceleration like this? This is my centripetal, and this is my tangential. Then the total acceleration looks like this. Right? Okay. What's this car doing? It is changing direction, and it is speeding up or slowing down? Why is it speeding up?
To be able to go up the hill.
Well,
But which way is the car going? The car is going this way, and it's accelerating that way, right? So therefore, it's speeding up. Okay, but what if it was accelerating this way tangentially? And this is the centripetal. Now it's slowing down because it's traveling this way, but it's accelerating in the opposite direction. That means slowing down, right?
right.
Okay, everybody, total acceleration is the translational acceleration plus the centripetal acceleration squared and square rooted, because they're vectors. It's a squared plus b squared equals c squared to get the total acceleration. Okay?
So it's funny because when I see it like that, it makes me think it's lift off.
It's going to lift off and go away.
But so if that's like there for a long time.
Yes, but it won't. Yes, that's correct.
I'm gonna do that.
That's correct.
And sort out hurricanes.
All right, we out of time?
Who's trying to?
Okay, we're out of time.